Hello, everybody. My name is Siddhartha Das. Today, I would be delivering a talk on my recent results on electrokinetic transport in polyelectrolyte brush functionalized nanochannels and all-atom molecular dynamics exploration. I'm an associate professor in the Department of Mechanical Engineering at the University of Maryland. Before I start the talk, I would like to extend my most sincere thanks to Dr. Bhatia, to Dr. Thareja, and Dr. Ghosh for kindly inviting me to participate in this meeting. So the essence of this talk is understanding how functionalizing nanochannels with polyelectrolyte brush molecules affect the electrokinetic transport in such nanochannels. So to move forward, we would like to understand what are polymer and polyelectrolyte brush at the very beginning. So polymers, as we know, are long molecules, long chain-like molecules that have individual constituting monomers. Polyelectrolytes are those polymers where those constituting monomers might be charged. Now, when polymers and polyelectrolytes are very densely grafted to a substrate, dense enough so that they, in order to avoid their adjacent polymer molecule, polyelectrolyte molecule, extend vertically away from the grafting surface, it leads to the formation of polyelectrolyte or polymer brush, the bristles of a toothbrush, that kind of a structure. Now, where such brushes are important? These brushes, these polyelectrolyte polymer brushes, are omnipresent in a wide variety of applications. For example, let's say nanoparticles. Nanoparticles are often designed with this kind of polyelectrolyte brushes. Examples of, let's say, a nanopore, which have their internal walls grafted with this kind of polyelectrolyte brushes. And these brushes respond to the surrounding stimuli like the salt concentration, the pH of the solution that is moving through the nanopore. And accordingly, utilizing those responses, people can devise a large number of applications like nanosensing, sensing of small molecules, fabricating nanofluidic diodes, and many more. In this present study, we will talk about how these polyelectrolyte brushes, when grafted to the inner walls of a nanochannel, affect the electroosmotic transport. And we will provide a molecular scale perspective of this problem. To begin with, let us first quickly introduce what is electroosmosis in a nutshell. So typically in a charged micro nanochannel, that is nanochannel or microchannel with a charged walls, in order to nullify those charges on the wall, there is a development of a double layer of electrolyte ions, where there is, and inside the double layer, there is an intrinsic charge density, that is the charge density gradient, that is the number of plus ions and number of minus ions are unequal. Typically, it is found that if it's a negatively charged wall of the nanochannel, the number of plus ions, also called the counter ions in this case, would be more. As a result, when we apply an electric field, there is more amount of motion of plus ions within the double layer. That in turn draws the water molecules with them, and we get this kind of a plug-like profile known as the electroosmotic flows. So basically, what triggers electroosmotic flow? These are important information. Number one, the presence of this kind of a charge imbalance within the electric double layer, application of an external electric field, and the consequent motion of the ion. So basically, you can see that the electroosmosis is invariably a counter ion motion dominated phenomenon. What happens when you have grafted polyelectrolyte brushes on such surfaces? There, at that point, you find that those brushes, they distribute the charges within the electric double layer. They control the electric double layer. So such alteration of the electric double layer gets reflected in the corresponding flow profile. Also, the fact that the brushes exert an additional drag on the flow would mean that under certain circumstances that the flow can be reduced as well. we would study this electroosmotic flow in polyelectrolyte brush grafted nanochannels at an atomistically resolved scale. So before going to look into the nanochannels perspective, we first developed this all-atom molecular dynamic simulation model to capture the behavior of polyelectrolyte brushes grafted at a single interface. The details, we considered water to be modeled as SPC water molecules, SPC molecules, SPC model, and we considered chloride ions. Sorry, we consider sodium ions as the counter ions, screening the brush charges, and also we considered additional 0.1 molar sodium chloride salt. Interestingly, this is one of the first molecular dynamic studies that probed the detailed microstructure of the polyelectrolyte brush molecule in an all-atom MD setting. So what is a microstructural understanding? That is where you no longer just consider the behavior of the polyelectrolyte brushes, but you also account for the detailed structure, distribution, properties of those brush-supported counter ions, here sodium ions, how the salt ions get affected by the presence of the brushes, and the water molecules that are solvating the ions, solvating the charge functional groups of the brushes, and so on. So a very detailed structure is obtained. While we don't go to the details of the water and the ion distribution in details, but we can quickly do a sanity check to see whether what we have got in terms of the brush profile, brush height results make sense. We find that based on the numbers of the ion density and things like that, the brush will be in a non-linear osmotic brush regime very quickly. We know that the brush height is typically dictated by the balance of the elastic extruded volume and electrostatic EDL ion energetics. Osmotic regime is where the osmotic pressure of the EDL ions balance the elastic energy of the brushes. Now, we find here, as you can see, that the scaling law is nicely reproduced by our MD simulations. Similarly, the monomer distribution that we find is a kind of a step-like profile, very much similar to the coarse-grained models obtained, coarse-grained result by Zaska et al. So, with the sanity check of the of the behavior of the MD simulation result of the polyelectrolyte brush molecules after a single interface, we go to the actual problem where we are looking into the electroosmotic transport in brush grafted nanochannels. Again, here we have a nanochannel, so we have brushes on both sides of the wall. We apply an electric field and we study the migration of the water molecules as well as the ions. Here is the main result of this manuscript, of this work. Beg your pardon. The manuscript got published in SES Nano this year. So the main result is as follows. We find that for low to intermediate electric fields, for a nanochannel with negatively charged brushes and a positive electric field, you get an electroosmotic transport that is from right to left, that is in the direction of the motion of the co-ions. So for the first time, we obtain what is known as the co-ion dominated electroosmotic transport. This is a most outstanding and significant finding. So far, people have already typically thought of that, except for the cases where there are some kind of a multivalent driven overstraining, etc. The electroosmotic flow would be typically a counter ion dominated event. Here we find that for low to intermediate electric field strength, it is a co-ion dominated phenomenon. On the contrary, for a large electric field, when the electric field is 1 volt per nanometer, the phenomena is a counter ion dominated. It's the standard counter ion dominated phenomenon. The question is why this is happening. The reason for its occurrence is what we identify as the overstraining at the low to intermediate electric field strength. Overstraining within the polyelectrolyte brush layer. What do I mean by that? So the polyelectrolytes are negatively charged. So to screen those, there would be more number of positive counter. There will positive counter, the sodium counter ions. We have added a salt as well. We find that there are more number of sodium ions inside the polyelectrolyte layer than needed to screen their charges. That's called the overscreening. As you can see from on the contrary, So on the contrary, what happens then to the inside the bulk, inside the brush-free bulk? And within that location, because of the fact that there are more number of sodium counterions within the brush layer, inside the bulk, you will have now more number of chloride ions. That is, there are more number of co-ions inside the brush. Hence, sorry, outside the brush, inside the brush-free bulk. Hence, when you apply electric field, these co-ions within the brush-free bulk is the dominating transporting factor, and that leads to the electroosmotic flow being driven by the direction of the co-ion motion in presence of the electric field. At larger electric fields, on the other hand, as E equal to 1 volt per nanometer, there is no more overstreaming, and hence there are equal number of plus and minus ions within the brush-free bulk. So there is no overstreaming and hence no co-ion dominated electroosmosis for larger electric field strength. The question is, why this overstreaming? There is, firstly, we identify that the overstreaming is occurring because there is a confinement. It's a nanochannel. For example, if you have a case of the polyelectrolytes after a single interface, the one we started with, there is no overstreaming. Why? Because nano confinement increases the osmotic pressure in the brush-free bulk. So there is a tiny gap of this bulk, brush-free bulk, where you are now pumping the salt ion, so the osmotic pressure goes up. So it basically now wants to relax that osmotic pressure. How to do that? The ions would move inside the brush. Now the natural question would be, then if such is the reason, then both sodium and chloride ions will move. Here only sodium ions move because of two reasons. Number one, sodium ions are much smaller than chloride ions, so it's much easier. Sodium ions experiences much lesser static hindrance, so it will move in. Second, sodium ions, because of its very large charge density due to its very small size, will very favorably now, due to electrostatic interaction, will replace the hydrogen from the COH form to form COO minus Na plus. So that hydrogen gets replaced by the Na plus. In that way, it becomes more stable. To understand that this only sodium ions does such a thing, we identified, for example, case what happens for cesium fluoride. For the cesium fluoride, we find that the cesium does not show that preference for both the reasons that it is not as small as sodium. Also, it doesn't have such a large charge density so that it cannot get stabilized by forming CO minus CS plus. We also check the stability of the sodium inside the polyelectrolyte brush layer, and you see this kind of you can see this kind of a small, the minimum inside the brush layer, localized minimum inside the brush layer for the sodium ions. No such minimum exists for the chloride ions. So this says that sodium ions can be highly stable inside the polyelectrolyte brush. Overstreaming is a very generic phenomenon. We identify such kind of overstreaming for a grafting, for a different grafting density, for a different salt concentration, for a different brush molecule. All these quantifications were done for polyacrylic acid. Previously, we did it for PMMA, polymethyl methacrylate acid brush. Same phenomena is always occurring. So we have overstreaming that due to the nano confinement and ion specific effects. Nano confinement leads to high osmotic pressure, which induces overstreaming. Ion specific effect means small ion size, high charge density, which favors overstreaming. Next, we look into the case what happens for a large electric field. For the large electric field, we find that as you apply the large electric field, the ions, the counter ions, try to get aligned in a given direction of the polyelectrolyte brush molecule, and as a result of which there is a lowering of the brush height. So you could see this leftmost plot where we plot brush height as a function of the electric field, and the brush height goes down. And as the brush height goes down, those polyelectrolyte molecules, the polybrush molecules, gets compressed, and in the process it pumps out all the ions. So the overstreaming is no longer valid anymore, is no longer existing anymore. So here is a scenario for large electric field. There is no more overstreaming. So there is no imbalance of the plus and minus ions in the bulk. So if there is no plus and minus ion imbalance in the bulk, what is causing the electroosmotic flow? We checked the ionic velocity and mobility. We found that at large electric field, there is no difference in that as well between the sodium and chloride ions. So then we went and checked for the residence time of water inside the solvation shell of both the sodium and the chloride ions, and found that the residence time is much larger inside the sodium ion for both the large and the small electric field strength. Small electric field strength doesn't matter because overstraining dominates there. Here, what dominates, on the other hand, is the case of the large electric field, and the fact that in the large electric field, this residence time within the residence of water molecules with the sodium ions is much more than that of the chloride ion. Residence time being more, that means it is more favorably drawn, the water is more favorably drawn, and hence you get a counter ion dominated electric field at larger electric field strength. Counter ion dominated electroosmotic flow at a larger electric field strength. So we have identified these key things. From low to intermediate case, we have the overstraining and hence a co-ion dictated electroosmotic flow. On the other hand, for high electric field, we have a higher residence time and hence higher residence times of water molecules. That phenomena dominate. So a counter ion dictated electroosmotic flow. Quick summary. I'm running out of time. So we discover monovalent counter ion mediated overstrain, polyelectrolyte brush and nanochannels. This overstrain coupled with larger ionic co-ion mobilities triggers co-ion mediated electroosmotic flow for low to intermediate electric field strength. At larger electric fields, there is no overstraining, and the electroosmotic flow is caused by the greater residence time of water inside the counter ion solvation shell. Very quickly, I acknowledge my collaborator and my students and US Department of Energy for funding this project, as well as the Deep Thought 2 for the computational resources. Thank you, and questions.